It started anyway. All right. Let's finish up the problem we talked about last time, kind of do the interpretation of what's going on, and we'll do a couple more applications. One will be for circuits, and one will be for chemical equations. All right, so we set up this set of equations with the traffic flow here, or whatever, flow pipes, traffic, it doesn't really matter. Remember, the principles that we were using to set up our equations is that at each of these nodes, what's going in has to equal what comes out. That was how we got our system of equations. Again, notice here that we've got 4 equations and 5 unknowns. So when we do our put in reduced row echelon form, you're not going to have enough information to get a single solution for everything, right? Because again, as we get pivots would mean that if we have a pivot in a column, we know exactly what that particular variable would be if we had one all the way down for every column. We can't get a pivot in every column. We don't have enough columns. We don't have enough rows to get a pivot in every column. Okay, so we'll get infinitely many solutions as far as the system goes. Let's see if I can put this in the calculator here. So we set up this equation last time. And what is going on? There it goes. So going to our matrix here, we've got, again, 4 equations and 5 unknowns. So I'll need a 4x6 matrix here to enter everything in. Right, I need the 4 rows for the 4 equations, a column for each of the variables, and then a column for the constants. What's the first row going to look like as we go across? What are your entries in the first row going to be for your matrix?
1, 1, 0, 0, 0.
Okay, good. 1, 1, 0, 0, 0, and then 50. Oops. And apparently I hit the wrong button. Second row.
1, 0, 1, 0.
Good. I'll write these down as we go along. So our first row was 1, 1, 0, 0, 0, 50. The second one was 1, 0, negative 1, 1, 0, 40. All right. Okay. What about the next one?
0, 1, negative 1, 0, 1, 60. Negative 1 is a positive one.
The positive one, isn't it? Yeah. And then 60. And then the last row will be
0, 0, 0, 1, 1, 50.
good. All right. So let me get those put in the calculator here. 0, 1, 1, 0, 1, and 60. And the last one was 0, 0, 0, 1, 1, 50. All right. So let's get back out of here. Not math. Go back over to your math menu. We want reduced row echelon form of matrix A. So put this in. Oops. It's hard for me to write and do that at the same time. Just put on the screen here. All right, so we've got 1, 0, negative 1, 0, negative 1. And I can't see the other one, so I'll write it down and then I'll scroll over. 1, 0, 1, 1, 0, 1, 0, 0, 0, 0, 0. Oops, not quite. Missed a row. All right, this over and scroll a little bit. Negative 10. Grab it. There we go. Negative 10, 60, 50, 0. Okay. Sorry about that. Get that on there. It's hard to go back and forth with the calculator when I have a screen and everything's small on mine. All right. Which variables do we not have information for? Which columns don't have a pivot. And certainly the last one doesn't, right? They don't have a pivot here. What else doesn't have a pivot? F3 also doesn't have a pivot, right? Remember, you got a pivot here at F1, here at F2, here at F4. I'm missing F3 and F5. Okay, so F3 and F5 will be our free variables. So we'll give them parameter names. So notice this, we're not getting a single solution for the flow. So your flows can vary, but there will be some constraints that we can put on the flows through the pipes as we do go along. All right, if F5 is equal to T, what does F4 have to equal? 50 minus the T, right? So again, when you put your T in for the F5 and you subtract it over, right? So 50 minus T. What does F2 equal? Good. So again, we would put S in for, here, looking at the wrong matrix. Put S in for F3, T in for F5, and subtract over. So you got minus S minus T. What would be F1 then? Good. Okay. We okay with reading the solutions all? All right. Now let's see if we can put the answer in context. These are flows. Can flows be negative? No. Well, if the flows were negative, we've been talking about going the opposite direction, really, I suppose. But typically speaking, our flows can't be negative, right? Otherwise, we would have had the arrow pointing the wrong way when we set up our equations. Is what that would mean. If our flows can't be negative, what constraints do you have on S and T?
S plus T are greater than 10.
Okay, well, that's true, but you jumped ahead of me for one. But if it literally just had S and just had T, what would it have to be? You have to be greater than 0, right, for certain? Okay. You went up to the first equation. Austin's exactly right. Looking at the first equation, what has to be true about S and T? It has to be greater than 10, right? Or S plus T has to be greater than 10. What would the second equation say?
Less than 60.
Yeah, the S plus T would have to be less than 60. Right? We know that our S is positive, or non-negative, I guess it should say, and so is T. Finally, the F4 equation, what does that say? Good, T has to be less than 50, right? So, perhaps you wanted to kind of visually represent this to see what your possible flow values could be for these. I can actually graph this in terms of S and T, right? If I make an S axis and a T axis. Yeah. I know that I would be in the upper quadrant here, right? The first quadrant. S plus T has to be greater than 10, or T minus 10. T is equal to, or T is greater than T minus S. 10 minus S. Good grief, I can't talk today. 10, 10. I'd have the same thing for less than or equal to 60. So you'd have another line this way. Ooh, hey. Right? And what else do we have? Your T was less than 50. So you'd have 50 up here and another line going that way. And pretty much then anything in this region is a possibility for S and T. Just gives you a little bit of a visual representation. If I pick a point in here, it'll work. If I pick a point outside of that region, it won't work. And give you a solution region, if you will. I did it because I could, because it was two-dimensional. Obviously, if you get more dimensions, you won't be able to do it graphically, but I just thought I would show at least a little bit about what the region might look like. One of the reasons why I wanted to do this is not an application we're going to do this semester because we just don't have time, but there is an entire subset of linear algebra called linear programming, where you're trying to either maximize or minimize a function based on constraints. These would be referred to as the constraints, And you might be trying to figure out where in this region maximizes output or minimizes costs or something along those lines. Okay. So there's a whole thing of a whole area called linear programming, and they do these kind of things. We had an alum a few years ago get a job at ADM and was doing lots of linear programming stuff for them. To try to, you can imagine why a business might want to try to maximize things or minimize things, right? Maximize how much stuff you can create for a minimum cost, for example. Yeah, Matt.
You know how you figure out which ones were S and T?
I have a pivot in column 1. I have a pivot in column 2. I have a pivot in column 4. Those are not the S&Ps. The free are the ones that don't have pivots. So there's not a pivot in the 3rd column, so I made that one an S. There's not a pivot in the 5th column, so I made that. Okay. Those are the ones that you can pick whatever you want. The ones that have pivots is once you've picked the values, you can solve for them. Yep, you're welcome. Yes.
You get a y s plus t has to be greater than 1.
Okay, so my F1 can't be negative. So I have to add something to the negative 10. That's why it has to be greater than 10. Likewise here, if I factor out a negative sign, again, F2 also can't be negative, so I can't subtract off more than 60. That's where those are coming from. It's coming from these two equations here. This one here is telling me that one. This one's telling me that one. All right. Other questions on this? Right. Let's do the next application, which kind of looks like this, but with a little bit extra. And that's the network applications. The circuit applications. All right. So some of you may have already seen circuit diagrams, depending on if you've had appropriate physics class or not. But notice that without worrying about the circuit diagrams, we see some flow things, right? Okay, so the I1, the I2, I'll give you this first example here. The I1, the I2, the I3 represent current, or a flow, if you will. Okay? So this one's saying the current's going around this way. This one's saying the current is, well, that one's going that way, and this one's going this way, right? Okay. Ignoring everything else in the problem, if we think about these as flows, you should be able to get a couple of equations set up. Here's a node. Here's a node. And just like what we did in the previous flow diagrams, current into a node has to equal current out of a node. Okay? So looking at this left node, what equation could you set up for when trying to solve for the currents here? What has to be true here?
I2 plus I3 equals 20 volts.
Not 20 volts. It equals the I1. Yeah, we're just doing it in terms of the current, right? The current in has to equal the current out. We're going to use the 20 in a second, but that says current in equals current out, right? What's this one say?
I1 equals I2 and I3.
Yeah, it equals I2 and I3. It literally says the same thing because we only have the two nodes, right? So those have to match. So I'm not going to write the equation again, but that node says it's literally the same thing, doesn't it? Okay. All right. So here's the idea behind how this goes, and this is where the 20 volts comes in. The current is going to be based on this these voltage. The longer one, when you have a long line and a short line like this, it represents a battery. This is the positive, this is the negative. So the if you will, the electricity is going to flow from the positive around to the negative. Okay. All right. So as we go around here, we've got 20 volts coming out of the battery, but these are resistors. That's what the little wavy lines tell us. And that's going to make the voltage drop because it's going to restrict the flow of the electricity through those things. So the idea behind this is that we use what's referred to as Kirchhoff's law. I think our Kirchhoff's law. I remember that. Yep, Kirchhoff's law says that when you go around your circuit, the sum of the voltage drops has to equal the voltage that comes into the system. Okay, so when you have a voltage drop here, it's the current times the resistor is how the voltage drops. This is what's adding voltage into the system. Okay. So if you pick it, by the way, you can pick whatever direction you want. I'm going to go around this way in my circuit. And if your current flows backwards, then we treat it as negative if we were going against we have the flow here. And that's going to pop up in the next one. All right, so go around this way. I hit this resistor. So the voltage drop there will be 6 times I1, whatever the current is, times the resistance. Coming around the other side, I've got another resistor. I'll have 6 times the I2, or excuse me, 4 times the I2. Those are your voltage drops. Every time you hit a resistor, it'll drop. Okay, that's the idea. I'm not going to go too much into the physics because I just want to get the equations set up. Okay, that has to equal the voltage that came in. 20. Okay. So far, so good? Okay. This one, again, let's think about orienting this way. Oh, and the only reason why I'm going around that way is because, again, I think about stuff coming out positive to the negative terminal, right? Come out of the positive, go to the negative. So it literally does not matter, except that if you go this way, that's not a voltage gain, it's a drop against it. You have to use that as negative because you're going backwards across the battery. Okay. All right. So what would the next one be here? Well, coming around this way again, I hit this one going the same way that the current is oriented, right? It says it's coming this way. So my voltage drop there would be 2I3. But as I come around to this one, I'm going backwards against its current, right? The way the diagram set up, it says I2 is going this way. Well, whatever way it is, that way for you. This way for me, that way for you. But we're coming around this way to try to resolve the diagram. So we'll make that negative 4I2. We'll use the negative to say we're going backward against the current, right? Okay. And that equals the voltage in the system for the battery. So now we have 3 equations to solve with 3 unknowns. A system of 3 equations with 3 unknowns. So pop back to the calculator. Turn the calculator back on because this emulator likes to turn the calculator off. And for some reason today, it really does not want me to hit the on button. On. There it goes. Here. All right. So what's the first equation that we have here? Okay. So what? How should we fill in our matrix entries then? If we use I1, I2, I3 for our first 3 columns, well, how should we fill out the matrix entries? So you're moving it to you're moving the I1 to the other side. That's fine. That's perfectly fine. Yep. -1, 1, 1, 0, right? That would be taking this equation here and subtracting I1 to the other side, right? You could have moved the I2 and the I3 over as well. Either or would have worked. Okay. What's your second row going to be? 6. Oops. You said 6, and then I hit the 1. 6, 4, 0. Good. 20. Good. Last row.
0, -4, 2, 10.
Good. Are we okay with getting the matrix set up without me writing it down? Okay. If you need me to write down, I can, but all right. Let me go grab the previous entry because all I want to do is row reduce that again. There's a solution. If you prefer to have it in fraction form, we can do that too. So the answers say what? What are I1, I2, and I3 in this case? Well, what are the answers? Sorry. You're right. They are fractions. I agree. But what are the answers is what I was asking for. Sorry. Your I1 is
40 over 11.
Okay. And the I2 is -5 over 11. Oops. and I3 is
45 overlay.
the negative sign here is indicating that the arrow is actually backward in the diagram. It's saying the I2 is actually flowing the other way. That's what the negative I2 means. Is that the diagram we set up the arrow going that way to get our equations, but really the current is going to the right instead of the left. Again, are we okay with getting the equations set up? That's the big thing. Let's just set up another system of equations again, make sure we got it. I won't take the time of putting it in the calculator because that is more effort than it's worth right now trying to get these things to go. All right, so let's look at this bigger one here. Bless you. Again, we have six variables. So if we're going to get a solution, a single solution, a unique solution, we better have at least 6 equations, and those 6 equations better tell us something different, right? Like, we didn't use the same equation twice in the first example, because both of them just said that I1 was equal to I2 plus I3. We only used it one time, right? But we should be able to get several different equations out of this, because not only do we have the 4 nodes here, you've actually got several circuits that you could do, and we could have actually done this in the previous problem as well. We've got these 3 smaller circuits in the middle, but you've also got bigger ones, right? You think about that bigger rectangle there, or that one, or the big one all the way around. So you've got a few. Again, we want to pick a direction. So we're going to go around the circuit to get our equations. And again, I personally like going from positive to negative, so we'll go around this way for that one. We'll go around, well, this one's harder because I've got 2 batteries in it that kind of cancel each other out, right? So it doesn't really matter. But so I'll just go in the same direction. This one, I got another 2 batteries that are opposing each other. I'll go just to keep the things the same. We'll just go in the same direction. Doesn't matter, just as long as you're consistent. You're just using it to get the equations. Notice that if I'm going to pick this direction to go around, I'm going to subtract 5 here, right? Does that make sense? Because then we're going backward against it, right? We're not going where the flow should go. Okay. All right, let's look at the nodes first and get the equations from the nodes. I've got 4 nodes in there. Using this one that I'm circling here, what equation do you get? Good. So the I1, because it's coming out, has to equal the I2 plus the I3. Go straight down, go to the bottom one here. What do we have? Good, I1 equals I4. Notice that we don't have another node until we come back down here again. So this I1 is going all the way around, right? Oh, yeah, it is the I2 as well. Yep, you're right. So it has the I2 and the I4. Good. Yep, because the I2 is also coming out. Thank you. This one here, upper right. This one here. Okay. And then finally the bottom one.
I6 equals I5 plus I4.
Do we see where those 4 equations are coming from?
Yeah.
Again, that's just from the flow, the same kind of things that we were doing in the previous problems, right? Again, this would not be enough information to give us exact, unique values for all 6 variables. We don't have enough information, right? We're going to need at least 6 equations. Okay. We should be able to get 3 more. 3 more is probably overkill, but let's make sure we have enough information to get all 6. Okay? All right. Yes?
What did you get? I6 goes to I5 plus
I6 goes up to here, right? So I6 is coming in, I3 and I5 are coming out. Because what goes in has to come back out again. All right, so let's use the first circuit here. Going around in this fashion again, going counterclockwise. Again, it doesn't matter if you go clockwise or counterclockwise as long as you know how to make your negatives work, right? Okay. Coming around this way, I hit this resistor, right? Coming around this way, I hit this resistor. That voltage drop is what? 10I1. I don't hit any other voltage drops, do I? So what does that have to equal? Hit that one, right? There's a 5. Go this way, I hit another 5 or 10, and this way I go hit a 5, don't I? 20. Yep, good. Agree? Okay. So we actually figure out what I1 is from that, but that's the equation, isn't it? Okay. Because those are your voltage gains as you go with the batteries. All right, let's do the next one. Again, I'm going this way. Let's do the voltage drops first. What's this voltage drop going that way? 20I3. This voltage drop going that way. 10I4. So notice I'm going around counterclockwise, right? Okay. What's your voltage gain here? 0. It's 0 because it's got the canceling out of the batteries, right? Notice this tells me that one of these is the opposite of the other constant, it's a negative constant multiple of the other, which really means that one of my arrows is pointed backward, right? If I subtract one of these over to the other, one has to be positive, one has to be negative. So it's telling me that one of the arrows is backward in the diagram, if you will, for which way it actually goes. Last one, going around that direction again. What's the drop this way? 20I6. Because I6 is the current here. Yep. And that's the only voltage drop. What's the gain? 15. Good. Because it knows we're going backward against the 5-volt battery. Now, are we okay with how we got those equations? It's also important. Is that okay?
The second one. Why is it not 10I3? Why not 10I1?
This one? I'm in this circuit here. That's my 10.
Wait, isn't
My
it?
I.
My bad.
Go ahead.
Isn't it 20I5?
I5 is on this one. We're hitting the resistor here. My I6 is that whole thing. This one here is the I4 is this line. That's where the 10I4 comes from. My I1's all the way over here. It's not in this circuit. Yeah.
So on the first equation, you have I2 plus I3 being positive, and they're going into I1. But then on the second one, I1, would they be going like out of I1? So why would they also be positive?
Remember, we just have to equate what goes in and what comes out. We don't have to worry about the positive and negative on that. We just need to make sure they're equated. Because I can make them negative just by flip-flopping which side of the equation they're on. If I made it negative, I could just move it to the other side. We're just trying to get the equation set up. I don't have to worry about the positives and negatives at the notes. I just have to make sure that what goes in and what comes out are equal. Right? Because if this one's coming, which one did you say this one?
Yeah.
So if that's going out and I made it positive, I made this one going negative going in, I would have the same idea here. If I make it negative going in, it's really telling me it's coming out the other direction. So I don't have to worry about the negatives that way. I just need to make sure what goes in and what comes out are the same. All right. Now, one thing, pardon me, one thing that you have to make sure that you're aware of, and when you're typing these things in, that something may not make sense later on. Notice now I really do have more information than I need, right? I don't want to just throw one out necessarily because it's possible that up earlier I've got two things telling me the exact same thing. What I'm saying is though, when you have more information that you need, when you do your row reduction, you should have rows of zeros at the bottom. That should just cancel out and tell you didn't need it. You should just have 0 equals 0. So if you don't get that row of zeros at the bottom, if you've got more information than you need, you've typed something in wrong or set something up wrong. All right, so let's see if we can put this in, hopefully. Once again, the calculator turned itself off. I don't know why I have to hit it 20 times. There it goes. All right. So in this case, we've got 7 equations that we've written. We have 6 unknowns plus the constant. So we'll have a 7 by 7 matrix here. Here's also a little quirk with your TIs, which is a pain in the butt, but we have to work around it. If you have a matrix with more rows than columns, the algorithm they use for the calculators to do your row reduction doesn't work. It'll give you an error. Okay? So if you come up, right now we have the same number, so we're okay. If you have a problem where you've got more rows than columns, fill in the extra columns that you would need with zeros on your calculator and then just ignore them when you're done. Because remember, when you're doing your row operations, you're going top to bottom. It's not going to change anything. They're always going to be zeros. But to get the calculator to work right, you have to zero fill in on the right. It's a quirk of the TIs. I don't know why it does it that way, but it does. Okay.
Wait, so you're saying
if you have more rows than columns. If you had something like that you wanted to row reduce, if you just close that off on your calculator, it's going to give you an error. So just fill it out for the extra column that you need, and then when you're done, just ignore it. Yeah, that's what I'm saying. Okay. It's a quirk with the calculator. Whatever algorithm they use to do row reduction in there will not do it correctly if there's more rows than columns. And I don't know why, because I don't know what algorithm they use. All right, what are we going to type in the first row here?
-1, 1, 1, 0, 0, 0, 0.
Yep, all the way across here. Okay, so notice this one. Oops, no, I'll go back. This first one's going to give you -1 if you subtract the I1 over 1, 1 for the next ones, right? And then 4 zeros and a 0. I did not leave myself nearly enough room there. Was that too many? Oh, it was too many. Thank you. It was one too many. I got a little excited. All right. How about the next row?
-1, 1, 0, 1, 0, 0, 0, 0.
1, 0, 0, 0. Yep. So move the I1 over again. You'll have -1 for the I1, 1 for the I2, 0 for the I3, 1 for the I4, and then zeros all the way the rest of the way across. Next one.
0, 0, 1, 0, 1, 1.
It's going to be -1, won't it? So you got to move the I6 to the other side. And then 0 again. Okay, so that one, if I move the I6 over, you'll have 0, 0, 1, 0, 1, -1, 0. Fourth row. Still there, I miss a little bit of room. Fourth row.
1, no,
What are you doing?
One. Wait, what is that? Negative 3 or? What is it? Oh.
What is going on with this thing? Being very cranky. There we go. Sorry. Being very mad at me for some reason.
Well,
Did you hit the new button?
No, I did. Thanks. Okay, great. All right, what's the next row going to be? Sorry. 0, 0, 0, 1, 1, negative 1, 0, right? Okay. What will the fifth? Let's just go ahead and fill out the rest of these rows as I go. What will be the fifth row?
0, 0, 0, 1.
Good. And the sixth row.
0, 0, 1, 10, 0, 0, 0.
And finally, the last row.
5 zeros, 20, 15.
We okay with how we're getting this matrix set up? I mean, it's the same stuff we've been doing, right? Technical difficulties aside. Okay. See if I can get these entered in here now. Fourth row was 0, 0, 0, 1, 1, negative 1, 0. Next one was 10. And a bunch of zeros until I get to the last column, and then a 20, 0, 0, 20, 10, 0, 0, 0, 4, 5 zeros, a 20, and a 15. Ah, finally. That okay? All right. So now we want to row reduce. We get the there, and I'll change it to a fraction. Maybe make it look a little bit nicer, almost. Okay. Notice what I was saying here about the last row being a row of zeros. I do see a row of zeros there, right? And notice we do get a single pivot in every single column, right? Okay. So looking at our answers, what's I1? 2. And I2 is also 2. I3 and I4 are, and I5 and I6 are 3/4. Okay. So basically I3 and I4 aren't doing anything. No electricity flowing through those. The process, okay. That's the important part here. Technical issues aside, are we okay with the process? If not, I can talk about it again, but it's okay? Yes, no, maybe. Okay. All right. Last application. Chemical equations. You may have already done this in a chemistry class. You may have shortcuts for doing things from a chemistry class. I remember I talked about this a couple of years ago, and I was told, don't have to do that, blah, 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 blah. I'm like, I don't care. We're just doing this to set it up to show you an application of the system of equations. Okay? All right. So we're going to do this very, very algorithmically. If you've got shortcuts to do it because you know things from chemistry, fantastic. I don't want you to do it that way. Okay? I want you to do it the way I'm telling you to do it because we're doing it as an application of the systems of equations. All right. So let's look at this first equation, first chemical equation. We've got, I don't even know the technical names for these different things, so I'm not even going to try. I know that's carbon dioxide. I know that's water. You got to remember, I haven't had a chemistry class since my junior year of high school, which would have ended in 1988. So I don't know these names for different compounds. Okay. So don't ask me because I don't know. All right. Great. We want to try to balance these. When we set these up, we will get an infinite number of solutions, by the way. But we will think about these in terms of atoms and trying to balance the number of atoms of each element on each side. So what we'll do is we'll convert the infinitely many solutions into one that makes sense from an integer solution standpoint. Okay, so that's what we'll get to at the end. All right, so notice here we've got 4 different compounds. So we're going to multiply these by 4 different constants. So I'll take an x1 in the first one. I'll do an x2 for the second one. I should have left myself more room when I did this. x3 for the first one, or third one, sorry. And x4 for the second one. Or for the last one. All right, so again, we're trying to balance number of atoms. You have to have the same number of atoms on both sides. But if I do anything that's with this compound here, somebody can tell me what the name is. I don't know what it is. If I do anything with that compound there, notice that whatever I have for x1, I'm going to get 4 hydrogen atoms. Right? Over here, my x4, I'll have 2 hydrogen atoms, no matter what I'll have to double what the x4 is, right? So we're going to set up our equations based on making sure we have the same number of atoms on both sides when we're done. Okay? So let's start with the carbon atoms. How many carbon atoms are on the left? X1. And how many carbon atoms are on the right? X3. So I'd have X1 equals X3. Okay. How many hydrogen atoms are on the left? 4x1. How many hydrogen atoms are on the right? 2x4. So those have to be equal. How many oxygen atoms are on the left? 2x2. How many oxygen atoms are on the right? 2x3. Okay. Everybody see where those are coming from? No? What's just causing the issue? Where do I get them? They're the very... Why did I put them in there? Because I have to have the same number of atoms on the left as I do on the right for any of the atoms that are in there. I don't know what I'm doing to start with, so I'm just making it a variable. I have to solve for what those variables are. So each of these, I can do any number of compounds of this. I can do any number of compound of this. And same thing on the right-hand side. I just don't know what they are to start with, so I'm calling it a variable. I don't know if it's 2. I don't know if it's 7. I don't know if it's 20. I have to make it a variable to start with, and I'm trying to solve for those variables. That's why. Okay. I've run out of atoms, so that's all the equations I get. So this is going to have infinitely many solutions, maybe fractions, but we know that our atoms are whole numbers of atoms. We're not splitting them, right? Okay. So when we're done, we will get a whole number solution based on the infinitely many we get. So let's see if we can make sense of that here in a second. So let me go back to the calculator. Hit the on button 20 times to see if it turns back on. Oh, for God's sake, what are you doing today? Why would I want to use a calculator? Clear. And it's locked up. Why are you locked up? Okay, let's try this again. About ready to go over to Desmos or something else because that's being a pain in my butt. Try to do it on the calculator so you can see what it looks like on the calculator. Hey, there we go. All right. In this case, I've got 3 equations and 4 unknowns, and then I also have a constant column. So this will be a 3 by 5. X1, and it'll be a minus X3, right? Okay. And then I don't have an X4, and the constant will be 0. Oops, I forgot my negative sign, didn't I? So your first row should be 1, 0. It's right on the board. Your first row should be 1, 0, negative 1, 0, 0. Right? What'd the next row be?
4, 0, 0, negative 2.
Okay, 4, 0, oops, 0, negative 2. Oh, I actually put the negative sign in there, right? 0. Good. So 4, 0, 0, negative 2, 0. And the last one,
0, 2, negative 2.
good. Oops. 0, 2, negative 1, negative 2, negative 1, 0. Good. We okay with the matrix? Okay. All right, so get back out of here. All right. So I got a negative a half, a negative 1, and a negative a half. All right. So let's see if I can remember how to do that. Sit. All right. So you've got, when you do your reduced row echelon form, this is what it looks like. At least I hope that's what you got. All right. So again, we get infinitely many solutions. We should get infinitely many solutions here because we have a homogeneous system. We have no constants, right? If you move all your variables to one side, you get a column of zeros. Remember, homogeneous systems always have at least one solution. If they don't have exactly one, then it has infinitely many. Okay? So we get infinitely many solutions. You should also make sure that anything that you're going to move to the other side, when you do your free variable, better be negative, because we can't have a negative number of atoms. Sure, that would do something bad to the space-time continuum if we had a negative number of atoms or something. Okay? All right, so these answers that you get here should all be negatives, okay, when you start to move into the other side. The free variable is your x4. That's the column that doesn't have a pivot. Moving things over to the right-hand side, your x3 will be what? Yeah, 1/2 the t, good. Your x2 will be t, and your x1 will be 1/2 t again, good. All right. That will be our infinitely many solutions. We want a whole number of atoms when we're done, right? If I want a whole number of atoms when I'm done, I want to clear these. I can pick, remember, infinitely many solutions means I can pick whatever I want for t. If I want a whole number of atoms, I want to plug something in for t that's going to cancel out your fractions, make your whole numbers. What should I plug in for t to make the 1/2s go away? 2, yeah. So, using t equal to 2, we get x1 is 1, x2 is 2, x3 is 1, and x4 is 2. So what was your equation then? If I balanced it, going back to what the equation was because I can't see it because it's not on the screen, you'd have CH4 plus 2O2 is CO2, oops, plus 2H2O. And that balances the equation. So again, you can do these very algorithmically. Put a variable in as your coefficient for each of your molecules. Okay? Put a variable in for your coefficient for each of your molecules. Set up your system of equations by equating atoms on both sides. Row reduce. Set up your matrix and row reduce. You will get an infinite number of solutions each time. You won't have enough information to get the exact solution to start with, which makes sense because if you balance a chemical equation, I could double the number of atoms. It's still on everywhere, and it's still balanced. I could triple it. I could quadruple it, right? You shouldn't expect to get a unique solution because there's not. There's infinitely many integer solutions as well, okay? The thing is, though, you want to make sure you do an integer solution. So when you get these fractions, you'll want to pick a value for t that cancels all your fractions out. So use the least common denominator. So for example, if this were 1/3 and 1/4 rather than halves, you would use 12 for cubes to cancel out all the fractions at the same time. Does that make sense? Again, you can do this very algorithmically. Like I said, I know there are probably some tricks to doing it more quickly than that. I don't want you to do the tricks. Okay? Do it algorithmically for me. All right? You got your homework due Monday, the sheet that I gave out, right? And you've got WebAssign, I believe, due on Sunday night as well. So, all right? Have a good one. Have a good weekend. See you Monday, unless I see you later this afternoon. Mm-hmm. So I'm looking at my carbon atoms. Yep. Okay. That's multiplied by x1. That's multiplied by x3. They have to equal each other. So that's at the same number of atoms. Yep. So that's where the 4 is. So this one is hydrogen. Anytime I have this compound, there's 4 hydrogen atoms. So if I have 2 of them, there would be 8. If I have 3 of them, there would be 12, and so on down the line. So that's why it's 4 x1. Yep. And then over here it's 2 x1 yeah, that's why it's 2 x4. Yeah.
Fix everything.
Yep. 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 Multiply by 2 there to get the 2 oxygens. But here we only have 1 oxygen, so it's just a single x4.
Hold on. So, does your school example work for you? It works.
2 times x3. Yeah. We're just multiplying it by the variables. Hi. Hi. Nice to meet you.
And now,
Yep. Okay. Okay, so this is the handout we were just working on last today. And this is the homework assignment I gave out last time. Make sure you get into WebAssign.
I read it like a week and a half ago. I know I should have.
Okay. Yeah, the book link's not working. I'll resend an email to you. I had sent it because
I made one.
Yeah. Quick one I'm thinking about it.
No, I applied for 8.
It's for some reason with Sim Days, they didn't do it. So there's not an access code.
I'm not there yet. You gotta apply for defense and internships. I don't think I'm there yet. I'm definitely defense contractors. Predator drones.
Oh, right. Predator drone. Yeah. Predator drone?
I just forwarded you the directions again. So it's our website. This is the class key you'll need to get.
Oh, okay. All right.
Okay. All right. Let me know if there's anything else issues with it. But okay. Okay.
Sounds good.
All right.
Thank you.
Oh, sorry. Because it brings up an error because I run mine, it doesn't give me the right answer.
Okay. So something's not typed in right. Oh, I see it. That should be -1. That one right there should be -1. That's why you're getting there.
Yeah, the first one we had to deal with exercise on 1.52. It's still like it didn't give the same answer you had before.
And my guess is there's just a, you can type in one thing wrong and it'll mess everything. It's just like if you do arithmetic error by hand. There you go. Okay, thank you. Yep. Yep, it was just that one. It's just that one missing negative sign messed it up. Oops, I forgot to stop that.